Good morning, everybody. This is Tricia Cease, President of the Virtual Foundry. Very happy that you joined us today for our Design for Additive Manufacturing with Filamet webinar. Today is Thursday, July 29th. It's 11 a.m. here in southern Wisconsin in the US, and we are excited to talk with you today. Joining me leading the webinar, as always, is David Lawson from Sapphire 3D. He's our sintering services partner. Brad Woods, founder of the Virtual Foundry. And then there's myself. You can see we put all of our fancy pictures up there. We aren't that fancy in real life. So we love talking with you and hearing about what you're working on all the time. A couple of notes about the webinar. This webinar is being recorded, and I will post the webinar to our YouTube channel later after the webinar is concluded. If you have any questions, please type those into the chat box. We will have a Q&A portion at the end of the webinar. So if you type your question into the chat box, we will take some time to answer those towards the end of the session. If we don't get to your session within the time today, don't worry, we will answer that for you in the follow-up email that I send when I send you the webinar link. So we will get to all of your questions. Now we're going to go ahead and get started. Today we're talking about design for additive manufacturing with Filamet. We're going to be covering how filament and plastic printing processes are the same, how they are different, designing for the sintering process, accommodating for shrinkage, and then we're going to have a discussion about generative design or topology optimization. And then there's that Q&A time I talked about. So let's go ahead and get started. First of all, we're going to hear from Brad and David about the similarities between printing with Filamet and printing with regular PLA plastic. So Brad, why don't you go ahead and get us started?
Sure. When we tell people when they first start to set the printer up with PLA, and this is if they haven't worked with our materials before, but get everything working with PLA, prove that you can print, and make two changes to the settings. And this would be like the default settings in Cura, for example. Just pick the default generic PLA and raise the temperature to 220-ish. I think it defaults to 200. You likely have better luck around 220, 215. And the only other change you need to make is the flow rate. What happens is our material is very viscous. So compared to pushing PLA through the print nozzle, it's a lot more like pushing bread dough through the nozzle. So we have people turn the flow rate up to about 140%, somewhere in there. Start with 135. You may need to go higher. You may need to go lower. It can vary a little bit by printers, but that's the easiest place to start. So my main point is the settings to print Filamet are not particularly unique.
I'll just add a couple things. Can you hear me okay or no?
Yes, go ahead, David.
Oh, okay. Yeah, very similar. In fact, I typically will go back and forth between Filamet and just normal PLA without really changing a lot. I'll just keep my Filamet settings like Brad mentioned. 220 is what I typically use. And then it's about getting that correct flow rate. I might tweak the height of the nozzle when I do my first layer calibration. And I sort of keep it tuned for the Filamet. And then the other thing typically will be just the, as far as the support material, like you indicate there, Filamet is great support material. I've experimented a little bit where I might have like certain layers or a raft or anything like that where I'll use PLA and then switch to Filamet. But in general, I like it as a support material as well if you don't have a ton of support, because then it just easily comes off.
So in addition to just using more Filamet as support material, you can also use regular PLA. If you got a dual extrusion printer, you can use regular PLA as your support material. You can use dissolvable supports as your support material. So lots of options there. Anything that you would use as a support material with regular PLA, you can use with Filamet. And then a key tip here is that you're going to, whatever support material you use, you're going to remove those supports before going through the debind and sinter process. So we talked about what's similar between printing regular PLA and Filamet. Now let's talk about those differences. The major difference between PLA and our Filamet materials is that the Filamet materials are sinterable. So all of our materials can be debound and sintered, aside from our carbon fiber. That is a standard plastic with carbon fiber included in it. So not that one, but everything else can be debound and sintered in common kiln equipment. So that's going to be the major difference. So Brad, David, talk us through the rest of these differences that we see here, and add any more comments about that sinterable aspect of our materials.
Sure. Sure, I can go first. As we mentioned, flow rate. This is the number one problem that people have when they're starting with our material is they'll send us a picture of their print and it'll be very, very under extruded. So this is a common issue, and just exaggerate it is our recommendation. One thing that's kind of interesting on the topic of overhangs, so our materials all have a high metal load. And so if we use like bronze or copper as an example, those are excellent conductors of heat. So what happens is you can actually print a more severe overhang with our materials than you could with plastic. Plastic is an insulator and it doesn't want to give up its heat readily. When you add the copper into it, it sinks the heat away from the print edge quickly enough that you can get, like I said, very dramatic overhangs. So you can get by in many cases with, using less support material than you normally would. And those points kind of apply to bridging too. One thing about PLA will have a tendency to sort of form a string when you're bridging between two different places. Filamet doesn't do that. Like I said, this goes back to more like the dough analogy. So bridging can take, takes a couple tries.
Yeah, and I've experienced what you're describing, Brad, with the overhangs and the bridging by just going back and forth with the same model using just PLA and then using your materials. That's a really good way. If you have something that has like some of those torture test prints, things like that, those are good ones to test the examples, the difference between the two materials. Just run it in PLA and then try it again with like a bronze or copper, and you'll see exactly what Brad's talking about.
And how does your retraction setting play into managing bridging?
Okay, it doesn't come up so much in bridging. Well, it could, but there's a side effect of the retraction that just kind of keeps things moving more smoothly. If you add a bit of retraction at some point in each layer, like maybe at a layer change or something like that, just the act of moving the material in and out just kind of keeps it moving more freely.
Okay, great, thank you. So again, any questions that you have, please type those in the chat box and we will answer those sort of as we go, and then also at the end of the session. So let's talk about designing for sintering. I think that might be why most people are attending today. We want to design so that we're getting a good part out of the end of it. So not only considering the capabilities of additive manufacturing, but also that post-processing that we can do with these parts. So in this portion of the conversation, we're going to talk about general part shape, wall thickness, holes and threads, channels and internal features, and infill. How important is it to have 100% infill versus 40%, say? So guys, talk with us about general part shape, additive manufacturing, and planning for that sintering process.
Right. One of the key things that's unique about this process, like we said, it's meant to be sintered at the very end of it. So all of the plastic that you put into the part while you're printing later needs to be taken out. And it leaves the part as a gas. So what can happen is if parts are very, very thick or walls are very thick, it becomes more and more difficult for the gases to escape from the center of the part, and it'll cause some distortion. We've done parts that are literally, 2 inches thick. And we debound them successfully, but the debind cycle was incredibly slow. I mean, I ran that one for about 24 hours, giving it that much time to get the gases out of the center. And for perspective, I have a couple of photos here. Tricia, could you turn on my screen sharing?
Okay, all set.
So here are a couple parts. These are quite thick. These are probably just a little under a ½ inch thick. So, and these will debind with relative ease. So I'm just trying to give people perspective on what we consider to be a thick wall. This is fairly thick and will need to be debound quite slowly. And this is a part, so sometimes people come to us, in fact, this is becoming more and more common. So these are just fixtures for something on an assembly line or on a robot or something like that. And this is coming up more and more often. So they need a quick part to solve their machine fitting and fixturing problems. But, milling it takes a lot of time. So the idea, 3D print it, be quick, get it done. And all of these are a bit too much. They take too much stress for even a good carbon fiber part. So they need to be metal. So these are quite clunky and chunky. Ideally, we would redesign these. So to be clear, I'm going to take these and I'm going to make this into a functional part for this customer. And we'll send it back to them. This is just a proof of concept. And then as I solve the problem, we'll share that with everyone on our website and in our forums. But ultimately, this would just be designed differently. So rather than having the big blocky chunks that are mostly there because of the way they used to be manufactured, which was on a milling machine or a cast, it would be better to remove as much of the material as possible and just minimize the amount of material used in the part.
Now, Brad, some of these prints have holes in the bottom and in the body of the print, and some of them do not. Talk us through that.
Right. So as an experiment, I'm trying it both ways. So we decided to just take this and do whatever it takes to get this part fabricated properly. So we're doing one with all of the holes in place, and then we'll do one that's intended to be more of a near net shape type of thing. So at the end, the user will just drill a few holes in it for precision.
So considering near net shape is important. If you've got some tight tolerances that you need to meet, this process should be considered near net shape. Drilling the holes after the fact is a perfect solution for making sure that your holes are exactly the right size. And that goes the same, for tapping threads. So threads may not center the way that you like them to, so tapping those threads post center is the way to get those exactly right.
And I've done it 2 ways. I've done it where, just like you see there, there's a blank and then you add the holes or tap them later. Or you print with a undersized hole and then you tap it. I've done it where I tap it pre-sintering, depending on, and again, it depends on the shrinkage if you can get that accurately. But if you're just kind of looking for like something that's in the ballpark, I've done it that way too. This material is very easy to work with before sintering, and then even after sintering, especially the bronze and copper, it's very easy to drill things out. So, and also Trish, you mentioned for example, on this part, it looks like there's like a piece that maybe is a stop or something like that. If that face needs to be perfectly machined, you can do that after sintering.
Yeah, you can machine before sintering. Also, I kind of wish I'd have taken a better picture of this. I think I have an example here. Yeah, I don't have a good picture, but I'll try holding it up to the screen. So this is 316L, and the flat shiny spot, I flattened it off on my mill. So you can it mills great pre-sintering. It's not gummy. You get nice clean chips off the cutting tool.
So talk about infill for a minute. We get this question pretty frequently. What is the requirement for infill for parts that you're going to sinter?
So for me, I've always worked with 100% infill. Now, when you start to get to really large parts, that's where this webinar is really important. We're going to talk a little bit later about like generative design and things like that. But I just, my experience, and I have done some things where I've tried to create like a thicker infill than like the slicer programs give you. Because if I just use like the regular sort of infill patterns and I say choose like say 40%, my experience has been that when I go to sinter that, I get a collapsing of the infill on the internal sections of the part. I don't know if you've seen the same, Brad, but what I've tried to do is like thicken up that infill, and then I've had some success using less than 100% infill. But if I can thin out the part or do some things with it so that the wall thicknesses aren't so thick, I'll just go with 100% infill.
One of the things that I've noticed is all of the major slicers right now, Cura specifically, they're designed to save time in the printing process. They're not necessarily designed to have high quality infill. So they'll lay down the infill lines only every other layer. So you get, a very poor print. I mean, it's good enough for infill, but it isn't good enough to sinter, and it'll tend to collapse.
Right.
If you dig around a little bit and use a different infill pattern, you'll find that, switch to something rather than the bicubic where it's at a 45-degree angle, use vertical lines. And we've printed parts all the way, we've sintered parts all the way down to, well, no infill, depending on the size. You can print a hollow part, and you can print things with like internal cooling channels and such. And I think you did that, right, Dave, for that Autodesk part?
I did, yeah. I don't know if on this slide or the next one we're going to talk about internal channels, but the thing that I found is that you can do that. And if all the requirement is that the cooling channel stays intact, for example, the design was a circle, but then after sintering, it sort of collapsed a little bit and became more oval shaped. You can, as long as you're still getting that cooling that they're looking for in the part, that's okay. Or another thing you can do, and I've experimented a little bit with this, is I will create a internal channel that's oval shaped with the longer part of the oval vertical. And then as that collapses, you get something closer to a circular shape internally. So again, that's a design feature that you can play with in your design.
So you're going through a first iteration, studying the results, and then adjusting your design based on those results.
Yeah, and pretty typical even of machining processes, as well as, my background had been in injection molding, and when they're designing injection mold tooling, there pretty much would always be a iteration process that you would go through. What I found with this material and the design of it and printing and sintering, especially on smaller parts, I can get to where I need to be in about 3 tries. And then after that, it's as long as I follow the process consistently, it's repeatable, very repeatable.
We talked earlier about that support material and how you were removing those supports before going into the debind sinter process. And we should mention that the part shape is supported by a refractory ballast. And we have different materials for the different metals that we offer. And we can tell you more about that offline. But we are using a sort of sintering powder, so to say, to support the part shape during the sintering process. So in that regard, if you have pieces of your part that are sticking out, or it's a tube, you're going to want to make sure that you have that refractory ballast, that sintering powder, inside the tube or inside any openings that are not closed off, that you can have access to, and get that material in there to help support that shape during the sintering process. Okay, let's talk about accommodating for shrinkage. So we have, people are asking us, how much should I scale my part to accommodate for shrinkage? So let's just start with that discussion there.
I'll have you take this one, Dave. You've done more experimenting with this than I have.
So what I recommend everybody does is, it doesn't take much time, but print your part. You know, what I've done is I will measure the X, Y, and Z right after printing, compare it to the model. And then when I sinter it, after sintering, I'll measure those same dimensions and then create a spreadsheet and just keep a table. And over time, you know, we've thrown around numbers like XYZ for bronze and copper of 5 to 7% shrinkage. And those are just really sort of general averages that we've seen across many different parts. The steels I've seen more like 10%, sometimes 15% early on, when, as you guys were increasing the amount of material, actual metal content. But I use those as starting points. So right now, if you said, here's a design, I'd like you to print and sinter it, I would probably do it at around, my starting point would be like 105% scale, XYZ. And then I would measure it, and then I would sinter it, and I'd see where I'm at. And this is the iteration process. So then I might say, wow, the Z shrank more. So maybe I'll take that into account in my next trial. And then eventually you get to the point where, depending on what's critical in your part, you're actually getting very close, again, near net shape, but getting very close. And maybe you just have to do a little bit of sanding or machining to get exactly what you need. But that's kind of been my approach with the XYZ.
Right. And this might be helpful to some people as they're trying to envision this. But the force that drives the shrinkage is actually surface tension. So you know, some people call it atomic diffusion. So it's the particles welding to one another, and then it's the power of the surface tension that causes the whole part to shrink. So that being said, you can actually control the amount of shrinkage. Shrinkage and density kind of go hand in hand. The more dense you want your part, the more you're going to need to shrink it, and you can do this by raising the temperature or extending the sintering time.
Right, so there's that relationship between density, shrinkage, and part shape as well. So the more dense you want your part, the more it's going to shrink. And then also the more subject it is to the part shape warping a little bit as you continue to shrink it. So all of those things need to be considered as you're thinking about your part design, and after you've done a couple of trials to see how the part comes out, and then making some adjustments to that design up front. Guys, talk about circular channels. David, you had mentioned this a little bit earlier. You've got a circular channel or any kind of channel in your part. You center it, and perhaps that sags a little bit. So you can accommodate for that in the design as well.
Yeah, and I also think, you know, the size of the internal channel can make a difference as well. I mean, if we've had some people approach us and they've had really small channels, and unfortunately I told them it's going to be difficult to measure internally like what the change was. But like I said, for me, with the ones that I did, those Autodesk ones, those were about a 1/4 inch diameter internal channel. There was a definitely sagging in that part, in that channel, but then we were able to address it by just some design tweaks.
And talk to us about circles. I know you've said in the past that circles hold their shape really well.
Definitely when centered vertically. So like if you've got a tube and you just are able to fill that, make sure you fill that tube with the refractory material, but they seem to come out very, almost very close to their design dimensions, as well as hold their shape very well.
Right. And what you're describing makes sense when you think of the densification process in terms of surface tension. So if you were to picture this process happening in zero gravity and you just took it all the way to the point where you melted the metal, you would wind up with a perfect sphere. So
right.
There are greater forces, like in a cube, the very extreme outer edges of the cube have more force on them than the parts that are more of the spherical shape.
Yep.
And we keep foreshadowing a little bit here on the generative design concept, but the generative design strategy solves nearly all of the problems that we're describing here.
I wanted to ask a question about outcroppings. This one is very interesting to me. If you've got a part, and Brad, the part that you showed earlier can be representative of this, where you've got a thicker section of the part and then you've got a thinner section of the part. So in the one that you showed, that bracket piece, we could see that the base was thicker and at the top it just had a thin part to it. Will those different areas of that part center differently? Do we need to think about how one piece or one section of it is thicker, one section of it is thinner?
Yes, there's you made multiple points there, but the most crucial factor on this topic is the time that it takes the heat to absorb through the part that you're sintering. So thin outside edges, I mean, they're going to get hotter quicker than dense parts that are in the middle. So this is more a property of sintering and thermodynamics than it is of 3D printing or any of the materials themselves.
It's definitely something just to be aware of in your design and to see, is there anything you can do to minimize that or to more, and I guess we'll get into this with generative design, to make sort of wall thicknesses more uniform.
Right, well, let's dive right into the generative design topology optimization conversation. So we can see in the upper left here a part that was designed to be manufactured through the machining process. It's a block and it's had material taken away from it. Now, as we move forward, we're seeing that material is being taken away, but we still have the fastening holes there everywhere that they should be. And then we continue that process until at the end, we have a that has strength where it needs to have it and no other extra material. This shape lends itself really well to additive manufacturing and to the sintering process. This is a topic I'm personally very excited about. I think things are going to be looking very different as we go into the future. So David, Brad, talk to us about how this generative design and the resulting parts would behave in the sintering process.
Actually, I want to go back a little bit further, and nearly every part on a car is designed to be not only for its function, but also how it's manufactured. So, I mean, and all machines are like this. So we need to change the way we think about this stuff a little bit. So Autodesk is kind of pioneering on the generative design stuff right now, and they're doing some really interesting things. So rather than, I mean, obviously you need to tell the drawing where the holes and things like that go. But beyond that, you tell in Fusion 360 anyway, you draw the shape, and then you go to each of those points and you tell it what kind of forces are going to be put on it, what direction the force is going to be, how many newtons of force, whether it's lateral, shear, that kind of thing. And then you hit go, and it will sort of organically grow it. So these parts start to look more like trees and things like that. And you'll notice in the final one on the bottom right, there are no large blocky parts. There's only material in the place that you need it, and it only supports the forces that it's going to have to endure. And it's just part of what makes it a little bit easier on the sintering side of things is there are no very, very thick walls. And you'll notice they all tend to look somewhat cylindrical.
And yeah, what I would add to that is, and it's been my experience, that very large blocky part at the beginning will have distortions. You've got to get the gas sort of out of that part, the plastic, during debinding. And so you think about the thin wall by those holes on the perimeter versus the thick part internally, the heat dynamics are going to be very different. You look at the part at the end of the sort of generation there, and my experience with those types of parts is they can sinter very consistently, and especially when you start to put in like these sort of circular tubes and rods and things like that, those sinter really well. So it's definitely where the industry is headed anyway. Just like you said, it needs to be from a design standpoint, also material savings and things like that, but it goes along with the sintering process really well.
And I wanted to go back to the part that I was showing earlier. Tricia, it's saying I can't share while you're sharing. Okay. So let's go back and take a look at this part again. So this is a big block. You can tell that this was designed not with additive manufacturing in mind. This is likely how this part has been made in this factory for the last 20 years or whichever. So I'm going to take this and make this into a functional part for our customer, just to show how it can be done. But I'm also going to take this part and redraw it and then generatively design it. So as I hand this back to the customer that we're developing this with, I'll give them two versions. I'll give them the one that they handed to me that was meant to be milled and machined, and I'll hand them another version that's additively or generatively designed for the AM process.
So rather than thinking about Filamet and additive manufacturing as a replacement to current manufacturing methods, which it can be in very many cases, we also get to think about new designs and new ways of making parts and even more material savings as we move from machining to additive manufacturing and then taking that a step further into generative design.
Right, and with the material savings is a crucial point because you're using so little material that you can use some things that are more expensive. So, I mean, you wouldn't think of machining a titanium part like this, but you're designed for this process. You're using 1/10 of the amount of material. So where previously titanium may have been prohibitively expensive and not make sense, it might make perfect sense from this perspective.
So we aren't necessarily the experts on generative design. It was important for us to talk with you about it, but there are lots of resources on the internet. Now, this article from formlabs.com talks about generative design, the basics of it, and also gives a list of software tools for generative design with Fusion 360 from Autodesk right there at the top. We do have a couple of questions on the board. Have you used infill line multiplier in Cura for an infill structure?
Yeah, I think that's where it just adds a line next to the other one. So yes, we've done that. So it just kind of doubles the width of it. The main thing is that some of the Cura infill patterns, like I said, don't print on every layer. They'll only print every other layer. So this trying to trying to save a little time, but undo that. The infill is very problematic when it's done that way.
Is there such a thing as too long of a debind sinter time for a certain part? Can you overcook a part? What happens then?
I happen to have one sitting here. So this is a piece of glass that I wanted to see what it would take. So this is a piece of sintered glass that is overcooked. It probably got both too hot and sat in there for too long.
So it's going to kind of start to melt and turn into a blob, right?
Yeah, it'll eventually, it will cause it, the longer it goes, and time and temperature, you kind of need to think of them as one thing. So like a time temperature profile. You can go longer at lower temperatures, you can go shorter at higher temperatures, vice versa, and all the other permutations of that formula that you can think of.
And I would throw the third variable, so time, temperature, and oxygen. So if you're using or depending on like a lot of these things we've been working with, like the carbon, the coconut shell carbon to inhibit the oxygen. What I've found, if you go too long, you run out of that material and then you oxidize the part. And you get either this black char on the part, or it just sometimes you'll get it where you run out too soon and it under sinters. You don't, it sounds funny, but you're overcooking, but it didn't you didn't get that necking like Brad's talking about, because you got an oxidation layer on the materials.
Yeah. So yes, with the longer the time period that you sinter for, the more of a challenge it is to keep the oxygen out of the equation.
So those are the questions that we have. Let's have, now we'll just talk about some resources. David, I know that you are able to help people with part design. Talk about that a little bit.
Well, I think the biggest thing is not so much on the like doing the design for people. If they have a design, I can recommend some things. More on a consulting role, looking to if there's certain projects people are working on a certain part or set of parts or something that's in their process, I can work with them pretty much from the design standpoint all the way through what we described today through the sintering process. So take on those types of projects with people on a project by project basis and work with them, kind of cradle to grave, just kind of get it all the way through. So, I'm going to be doing a lot of work more so. I've had a lot of success with the bronze, copper, and stainless steel. I'm going to be working with both artisans and educators on the bronze and copper. There seems to be a lot of projects and things in that area, and these materials really suitable for those applications. So,
Hey, anything else that you'd like to add, Brad?
Not that I can think of offhand. Other than that, we're on a mission here to have a recipe where people can 3D print, very common useful parts for fixturing and tooling. And I'm kind of picturing we're going to pick a size, say maybe 6 inches or less, and have a very simple step-by-step process that'll get people to a usable part in the shortest period of time possible.
Now we do today provide printing and sintering instructions on our website. So we do offer a process that will help you get started. If you are brand new to our materials, you're not, you want to give it a try, you're not fixed on a specific material, we do recommend starting with bronze. You've got the greatest chance for early success with that material. And we've got full instructions on our website. So you see on the screen here different ways to get a hold of the Virtual Foundry, different ways to get a hold of David at Sapphire 3D. So reach out to us. We're happy to talk with you anytime.
Also, I got one more thing. I could plug the, we have a server, we have a Discord server where people are sharing information and that kind of thing. There's good information on sintering there. There's people helping, users helping other users. And our YouTube channel has a lot on the topic also. So we share quite a bit of information there. So it's worth taking a look.
Great, thanks, Brad. I'll put links to both of those resources in the description of this webinar when it's posted to YouTube. All right, well, thanks a lot for joining us, everybody, today for our webinar. We look forward to seeing you next time.
Everybody.
Thanks, everyone.